Hey guys, welcome back to my YouTube channel. This is Ashok, and today in this video we are going to discuss about very important topic, which is transformer architecture. So this transformer architecture is a very powerful neural network model designed for a sequence data or sequence tasks, especially for machine translation. And it has become a foundation for many state-of-the-art natural language processing or NLP kind of use cases or applications. So this transformer architecture is introduced in the very important research paper called as the Attention is All You Need, which came in 2017. It is a groundbreaking neural network architecture that entirely revolutionized the NLP or the natural language processing. So without wasting much time, let's dig deeper into it. So before understanding the transformer architecture, right, so let's understand ANN, CNN, RNN and where this transformer architecture fits in. So this ANN is artificial neural network. And in this we'll see something about the neural network, how the neural networks are built. You will see something about activation functions. You will see something about the optimizers. You will see something about the loss functions. CNN is convolution neural network. Basically, if you want to solve any kind of image or any video analytics, right, you have a use case of solving your image analysis or a video analysis, right? In that case, you can use convolution neural networks or the CNNs. Coming back to the RNN, RNN is recurrent neural network. And if you are performing any text data analytics, right, specifically deals with the text data, right, in that case you can use RNNs. And RNNs, we can solve multiple use cases, like we can solve time series and we can solve NLP use cases. And inside this RNN, right, we have different architectures. So let's see what are those architectures. We have LSTM, long short term memory. We have bidirectional LSTM. We have GRU, a gated recurrent unit. We have something called as stacked RNN. We have encoders and decoders. Now this encoders and decoders plays a very vital role in case of your transformers, right? Then you have transformers, so which is our topic for today. So there is a research paper called as sequence to sequence learning, which was published in 2014, I guess. The base for this encoders and decoders is nothing but this sequence to sequence learning. So from here the advanced NLP story actually started. And the base for this transformers is this encoders and decoders. So this is the building blocks, or this is the components which are used in case of transformers. So there is one more component for transformer, is the self-attention, is called as attention mechanism. So this has come from the research paper, Attention is All You Need. So in this video, you'll understand the two key components, and they plays a vital role in defining a transformer architecture, right? One is the encoders and decoders and the self-attention. So guys, I want to dedicate today's video to this guy, J. Alamar. So he has given a very neat and very easy explanation of this transformer architecture, which says the illustrated transformer. So let's go ahead and understand how easily he has explained this transformer architecture, right? So he says the transformer, a model that uses attention to boost the speed with which these models can be trained. Now this is important, right? So it uses attention. As I told you, basically uses the attention mechanism or the self-attention, right? And he says the transformer was proposed in the paper Attention is All You Need, right? So what we'll do, in the coming videos, we'll understand the Attention is All You Need, this research paper, right? So if you want this research paper, you click in the view PDF and you'll get this research paper, right? So you'll understand this research paper in the coming videos, but let's understand this guy's easy explanation, right? So let's go ahead. So in a high level look, right, so he's mentioned in a machine translation application, it would take a sentence in one language and output its translation in another language. So basically he is talking about the machine translation or the language translation application. So he has taken small example, right? So what he has taken an input, right, in some language, and pass this input to the transformer, and it will result something which is nothing but output, right? So this is basically a machine translation or a language translation. So it provides input in one language and provides output in the other language. The same thing can be visualized like this, right? So you provide an input and you get the output, right? So this is a transformer. So as we saw, this is a transformer, right? So inside this transformer we have few components, as I told. we have encoders and we have decoders. So coming down, here you can see the encoding component is a stack of encoders. So now this encoder layer or decoder layer, right? So you can see 6 encoders stack, right, one after the other. So even same as decoders also. And he says this 6, right, 1 2 3 4 5 6, this 6 encoders is not a convention, right? You have to take 6 encoders, but he says like you can provide any kind of encoders, right? There is nothing magical about the number 6. One can definitely experiment with other arrangements. Now again, the decoding component is a stack of decoders of the same number. Now if you have 6 encoders, you need to have 6 decoders. Now this is very much important, right? So he saw that there is something called as attention, right? So you need to understand this attention mechanism or self-attention. So in the encoder layer, right, this is single encoder layer, and in the encoder layer again you have two components. One is the self-attention and the feed forward neural network, and the input to this encoder, right, it will be passed as an input to the self attention and then will be passed to the feed forward neural network. So here he is mentioning you have encoders and decoders, right? So this encoder is again two components, but if you see the decoders, you have one more component added, which is encoder and decoder attention. This is also very much important, right? So you see the input will pass to this, and the output of the encoder will be passed as an input to the decoder. Now this encoder and decoder attention, right? So the decoder has both the layers, same as self attention and the feed forward, but between them there is an attention layer that helps the decoder to focus on relevant parts of the input sequence. This is very much important. It focuses on the relevant parts of the input sequence. Let's move and see. So here he is bringing the tensors into the picture. Now if suppose you are working in any NLP use cases or textual data, right, your sequence of data, in that case those sequence of data will have words, right? So those words has to be converted to some format or some kind of numerical format, or you can say the vectors, right? So those vectors will be converted by using something called as embeddings, right? So that's what he's saying here. As in the case of NLP applications, in general we begin by turning each input word into a vector using an embedding algorithm. So this embedding algorithm, you will convert the input text or input word into an vectors. Now you can see here each word is embedded into a vector of size 512. Now you see input x1, x2 and x3, these all will be a vector of size 512. Now there is one more important point, right? So you can see the embedding only happens in the bottommost encoder. So you see here is a bottommost encoder, right? So the embedding, whatever you pass text data, you're passing to this encoder. This is the first encoder in the sequence, right? So this input data will be passed to the encoder, which is nothing but first one, and then the embedding will happen only in this particular encoders. That's what he's saying here. The input x1 and x2 will be passed to the self attention, and those will be converted to z1 and z2. These z1 and z2 will be passed to the each separate feed forward neural networks. So now here he is talking about something called as self attention, right? So guys, self attention, right? So you need to understand self attention to understand this transformer architecture, right? So this is very important component, you can say, or very important concept in case of a transformer architecture. So he has taken a small example here, which is basically a sequence of data, right? And you can say it as a sentence, right? So the sentence says the animal didn't cross the street because it was too tired, right? Now you understand there are two main thing in this one. One is animal and the street, right? And it says animal didn't cross the street because it was too tired. Now what this it refers to here, right? This is very much important. So what does it in this sentence refers to? It is referring to the street or the animal. So it says it is a simple question to human being, but not as simple to the algorithm, right? As a human being, I'll know this sentence, right? And I know, okay, animal was too tired, right? It cannot be like street was too tired, right? As a human being, I know that, right? But if you're passing the same sentence to the algorithm or the model, right, in this case it will be confused. So now when the model is processing the word it, or the algorithm is processing the word it, right, the self attention allows it to associate it with the animal, right? So self attention plays a very vital role. So here what it is doing here, right, so you can see this text, other text also, and it will try to find out the relationship between the words, right? So how they are related to each other. So that is where the self-attention plays a very important role. Let's take another example to understand this, right? You say My favorite phone is Apple. And somewhere in the sentence, it is written as I want to eat apple. So for you as a human being, it is understood, right? So you are talking, so in the first sentence you are talking about the phone, right? And in the second sentence you know that you are talking about something about the fruits. But this is very difficult for machine to understand or algorithm to understand, right? So machine here, it will get something called as ambiguity or some kind of complexity will generate, right? So to solve this ambiguity or your complexity, right? So this self attention will solve this kind of complexity or ambiguity. So let's dig deeper about the self attention and try to see how you calculate the self attention using these vectors, right? So the first step, calculating self-attention, is to create three different vectors, right? So there is something called as query vector, key vector, and the value vector. Now so the size of the query, keys, and values, basically this embedding, right? So this embedding is a 512 size, and this queries, keys, and value vectors is of size 64, right? So why the 64 is, again, this is the architectural choice or architectural needs, right? That's why they have used the 64 dimensionality. So in the first step, what you're doing here is you're taking the input, right, which is a text or a word, and then that word will be converted to x1, some kind of 512 size, right? Which is nothing but by using some kind of embedding algorithm. So what you are doing next is you are creating three different vectors. One is the query vector, key value, key vector, and the value vector, right? So these, how do you create these vectors? That is very much important. So what you are doing here, you take the input x1, you multiply with weight associated with this query vector, you will get q1, this q1, and this size of this q1 is 64. The dimensionality of this is 64. So again, that depends upon the architectural choice or the need of the architecture, right? So why 64? So you get this x1 multiplied with wq, you get q1, and similarly you will say x2 into wq, you will get q2, right? So x2 multiplied with wq, you will get q2, right? Similarly, you get the calculation for keys and values also. Now you came to know how you got this queries, key, and value vectors q1, k1, and v1. In the second step, what you are doing, you are going to calculate the self attention score or the attention score. So you're getting the score here. Let's see how you calculate that particular score, or that will be the attention for that particular word thinking. And this score determines how much focus to place on other parts of the input sequence as we encode a word to a certain position. So this is very much important, right? This particular score, what you're getting here, plays a very important role to get the attention for that particular word. Now how this score is calculated by using the multiplication of your query vector and the key vector. So you can say q1 into k1, you are getting 112. So similarly here, thinking how it is related to the machines, right? You say q1 into k2, you're getting some score. So the third and fourth step is basically to divide this particular score by 8. So now you'll ask me why 8, right? So this dimensions, what we told, is of a 64 dimensions, right? For this one, keys, values, and vectors, right? So you are taking the square root of 64 according to the algorithm or according to the architecture, right? So you get as 8. So you will divide the score by 8 here and by 8 here. So you will get, divides by 8, you will get 14 and you'll get 12. There might be different values other than 8, right? But by default, if they are taking at a square root of 64, you are getting as 8. Now this result will pass to a softmax activation function, right? So here it says softmax normalizes scores, so they are all positive and add up to 1. This is very much important, right? So you'll get 0.88 and 0.12. So if you add these two, you'll get as 1. So the fifth step is basically to multiply your softmax value which is generated, right? So this softmax value you'll multiply with the value vector. So this v1. So that's why you softmax into value vector, you'll get v1, right? Similarly here also you'll get v2. And the sixth step is basically to sum up the weighted value vectors. This produces the output of the self attention layer at this position for this particular word. For the first word, thinking, you will get this sum, you will take the sum of all these things and you will create a generalized z1. So this concludes the self attention calculation. The resultant vector is one we can send along with the feed for a neural network. So you can pass this particular calculation, whatever you got, right, self-attention, from the self-attention layer, you pass this particular score or sum to as an input to the feed forward neural network in the sequence, right? We understood this, right? So here you'll pass this particular pass to the self-attention, and then it will pass to the feed forward neural net. We already saw the matrix calculation, right? So you multiply it with the input with the weight of the query vector, and then you got this query vector. Similarly, you multiply it with x and wk, you get the key vector. X with the wv, you get the value vector. So whatever finally you are following this step 1 to step 6 here in this case, right? Same thing can be represented as this. You see, you use softmax here, then you use query, multiply this one, your multiplication will get here, this you divide it by the square root of 64, you get it here, and then you have the multiplication with the value vector, right, and you get the z value vector, and they get the z value. That's what it is represented here. So in the part 2 of this video, you'll understand something about the positional encoding. What is this positional encoding and why it is used? We'll mention something about the multi-head attention, because here in this case what we saw in this research paper is typically on the single head attention. We'll understand what is multi-head attention. We'll understand what is the add and normalization layer which is added on top of the multi-head attention, and also you'll understand about the linear layer, why it is used. Okay guys, that's it from my side for this particular video. So in this video you understood about the transformer architecture, right? So what is transformer architecture, how it is evolved, what are the key components of transformer architecture, and also he understood an easy explanation from J. Alamar, right? So that is illustrated transformer. Now again, I'm saying this video is dedicated to J. Alamar. Thank you for watching. If you really like this video, hit a thumbs up and please subscribe this channel, share with your friends. I'll see you all in the next video. Till then, take care, keep learning and keep rocking.